So now let's solve this very equation. What I'm getting? So I'm getting dpx by dt, that's equal to E times E. Then I'm having dpy by dt, that's equal to 0. Is it true? And dpz by dt, that's equal to 0. Clear? So now since initially I am assuming there is no momentum along z direction, so this will give me pz is equal to 0. Okay, because it could give me actually pz is equal to some constant value. Okay, so that will represent the momentum at the initial time. Okay, but I am saying there is initially no momentum along z direction. So what about this thing? So it will give me simply py is equal to p naught. Okay, and what about this thing? So it gives me px is equal to e naught. Okay, this e is electric field. Okay, so now let's write the energy of the particle in this in E. Okay, so what is that much? How much is that? So let's write as this epsilon is equal to root of m square c raised by 4 plus p square c square. So what is the, how much is that equal to? M square c raised by 4 plus, what is p square? P square is actually equal to px square plus py square plus pz square c square. Okay, so now tell me, so I can write it as like this thing, m square c raised by 4, py square is simply p naught square plus I will write simply p naught square c square plus, and there is a px square, this I can write EET square. Okay, and there is a c square, I will write c like this thing. Okay, and pz is equal to 0. So this very object, let me define it as epsilon naught. So let's write epsilon naught is equal to m square rather plus. So this is the energy of the particle at t equal to 0. Okay. So this will simply represent the energy of the particle at t equal to 0. Because at t equal to 0, you are having momentum only along y direction. Initially, the momentum is only along y direction. Okay? Clear? So therefore, I can write it as like this: epsilon 0 square plus CET. Okay? Now we are having the relation. I need to figure out the trajectory, is it? Okay, so what is the relation we know? So we have the relation between momentum and the velocity, like this thing. So this we have written last time, c square p divided by e. Is it? Clear? So let's write it. So what it gives me, Vx is equal to c square px by epsilon. So how much is that equal to? C square. What is px? What is px? So it's EET. EET divided by what is E? So it is root of this epsilon naught square plus C E whole square. So or in other words, I am having dx by dt, that's equal to c square EET by root of c. Okay, so now you integrate. Yes, any question? Huh? You integrate. So integrate. Okay, so I'm having now x of t, it is simply equal integration c square e t by root of c e t whole square dt. And we put constant of integration equal to 0. So समझा, we fix actually. So constant of integration, we take the initial condition in such a way that constant of integration is equal to 0. Okay, so what is the value of this very integral? Anybody? Can anybody tell me? Yes. So it will be simply root of this thing, epsilon naught square plus c t whole square divided by e. Okay, clear? So this is our x. ठीक है? let's write Vy. What is our Vy? So from that very relation, it is c square Py divided by this energy. So it is c square Py is simply P0 root of this epsilon naught square plus c t whole square. So just integrate it out. So you are having dy by dt, that's equal to c square Py P naught like this. Okay. So which gives me y of t as the integration of this thing c square P naught by root of, what is the integration here? Can anybody? So it is c P naught divided by e times e sine hyperbolic inverse c e t. Okay, so this is, so now we are having a parametric equation for actually catenary. So this is an x of t represented in terms of time, also y of t represented in terms of t, is it? So we are having two parametric equations. Now let's make a single equation. So let's from here, let's evaluate this very object CET here, this very point. So what I am getting, so from this very equation, I will be having y of t divided by CP naught, and then you put sine hyperbolic, that's equal to C divided by. Okay, so in other words, so now let's put this, so which implies CET is equal to this epsilon naught sine hyperbolic y by CP naught. This y means y of t. Okay, let's put therefore this x of t. Let's calculate the term this x of t in terms of y. So it is what is that? 1 divided by e times e root of, okay, what is c? So it is epsilon square sine hyperbolic square y by c. Clear? So what this is equal to, this epsilon square you take out, so it will be epsilon naught. It is 1 plus sine hyperbolic square, that's cos hyperbolic square, square and root goes, so it is simply cos hyperbolic. So this is the trajectory of a particle, of a relativistic particle in constantly uniform electric field, and the electric field is along x direction. Now you see the motion is in xy plane. Clear? So what is the curve called? So it is a catenary. Clear? So now let's take the non-relatives limit of this very objective. Okay? So first, before doing the non-relatives limit, let's expand this. Okay? So I can expand this cos hyperbolic. So I can write this as epsilon. So then I will take, so it's 1 plus e y by CP naught square. It's all that terms. Okay? Now when I take the non-relatives limit, okay, what does that mean? So V by C is very less than 1. Okay? So this is the non-relatives limit. So it means this P is equal to, let's say, mv. M is the rest mass. So it will be simply m times v. Okay? And what will be this epsilon naught? So it is simply equal to mc square. Clear? Because it will be simply the rest mass energy. Now let's substitute these values here. So there was actually an error in the last lecture. Huh? Okay? Last time we had an error here. So that's why I repeated this calculation. So it is x of t is equal to, what is epsilon 0 now? It's m, okay. M square PE, okay, plus half, so it is MC square divided by twice E times E, then you are having E square, this E square divided by C square. What is P naught? P naught will be simply MV naught square. Okay? So P will be simply MV and P naught I have written as okay, P naught is simply MV. That means it is along the y direction. Okay, so look here. So this is a number. Okay, this is a constant term, is it? So you are having a constant plus. So c square goes, m goes. So what you are having here, E times E divided by twice. Just tell me what will be here. So this m c square V naught square y square plus delta. Okay, let me write on approximately. Okay, I think there should be a series for 4c square should come. Okay, so now look here. So you are, oh, it's okay, there is no problem.
M
Now
square.
here, huh?
M square.
Yes, there is this m square. It's an m square. So it should actually twice m. Is this okay? Good. So now look here. So you are having E is also a constant. V naught is the initial velocity, is it? So this is a number here.
Yes.
Okay. So this is purely a number. So it means so x is actually proportional to y square. What this is? It's a parabola. Okay. So that means in non-relatives limit. Okay. Non-relatives limit v by c is less than 1. We are having a parabola. Okay. The trajectory is the parabola. This you know. Okay. Clear? Now let's move to the next problem. If you are having a charged particle in constant uniform magnetic field, constant uniform magnetic field. We are doing which cases? Latest particles. Okay. So let's take magnetic field B along. So we will consider the magnetic field along z direction. So its unit B is a constant thing and it's uniform throughout. Okay. So let's try it now. So the force will be entirely magnetic in nature. And this dP by dt is equal to E by C V cross P. Okay, so there will be no that E term. Clear? So now let's write. So you can now put as E by C. Let's write the velocity. So you can write I J K velocity. Let's write as Vx, Vy, Vz. So it is 0, 0. Clear? So I'm considering the velocity of the particle Vx, Vy, Vz. So that means I have particle is having all the three components of the velocity. Okay. Okay. Now let's calculate the component wise. Also, you have okay. So you are having this relation P is equal to this energy V divided by C square. Is that true? So this is the relation you already have at hand. Is it? So this is what we know. Here I can write therefore C square. Okay. So now let's calculate the component wise. So let's calculate the components in terms of the components. So I will be having x component. Let's calculate the x component here. So what is the x component? Vy multiplied by b. Okay, vz multiplied, so it is 0. So it is only Vy multiplied by b. Okay. So So it's epsilon by c square dvx. So it's equal to d by c v b. Okay, then you are having, okay, so this is x component, then I am having y component. So these are trivial problems, but you need to understand how to do these things. Minus e by c dx b, then you are having z component, so square dvz by dt, that's equal to 0. Okay, so this is how we do it. Now let's define a quantity, what we call the cyclotron frequency. So you'll understand yourself, but in a moment you'll feel like what exactly it means. Let's write cyclotron frequency omega is equal to ECB divided by this epsilon. Okay? Clear? Okay, you'll see. In a moment why we call it as a cyclotron frequency. So then I can write, now let's write these very equations. Okay, in terms of the cyclotron frequency, I will write this dvx by dt is equal to, now tell me, what you said? So omega vy, then I think dvy by dt is equal to minus omega vx. Okay, then you are having dvz by dt is equal to 0. Now look here, so these are two coupled differential equations. X and y are coupled. So you are having motion in xy plane as a coupled motion, but motion along z direction is independent. Clear? So much, okay. So let's first solve this kind of. So these are two coupled equations. How to solve it? You can, okay, if you differentiate it, let's say, let's differentiate it. What you will get? So you will get x differentiated. It is double derivative. And then dv by dt, so you will get here omega, so it will be minus omega. It will be simply the harmonic motion, is it? So if I differentiate it, so you are having d2. So this is one way to solve it. I will not do it. So it's omega dv by dt. So that's simply called omega minus omega vx using the other equation, is it? So these are two. So what kind of equation it is? So it is a simple harmonic motion, is it? Is it true? So that means you are having the motion in xy plane is actually harmonic in nature. Okay, so it's a kind of circular motion. So the particle follows a circular trajectory. Okay, so that's why we call this omega to be the cyclotron frequency. I mean, cyclotron is due to the cyclotron. I mean, it is a kind of frequency at which this particle oscillates, okay, or which it moves along in a given circle. So much more. Okay, so now let's do it the other way around. So this is one way to solve it. Now you know what is the solution of this very differential equation?
Yes.
A cos, okay, and A cos, let's say omega t plus b sine of omega t. Then you apply the initial conditions or the boundary condition to the problem. Okay, okay. So, but I will not do it in that way. Let's do it in this way. That will help actually. Let's complexify this thing. I will put like this thing. D by, I will map this to the complex plane. Okay, these two differential equations. I'll just map them to the complex plane. Okay, I'll make a phasor like this thing, Vx plus I Vy. This very object I want to solve. So that means it is actually this phasor that's moving in a circle on a complex plane, is it? So the tip goes along a circle. Now let's look here. So I'll put like this in Vx plus I Vy. So that means I am adding the two differential equations. This equation plus I times this equation. Okay. So that gives me Vx plus I Vy. So omega is a number. So you are having Vx. Sorry, Vy is here. Okay. Then you are having minus I Vx. So you can take minus I out. So it's minus I omega Vx plus I Vy. So that we now look here, it's simply now the linear differential equation for a complex variable, is it?
Yes.
So it is easier to solve than the second order differential equation. Clear? Okay, so now tell me what is the solution. So you are having now a differential equation of this form. Dy by dt is equal to, let's say, minus IAY. So now tell me what is the solution. So y is equal to simply some y naught e raised power minus I e t. Is that true? So is it true? So this will be the solution. So now tell me what is the solution of this differential equation. So it implies y is here what? Vx plus I vy, is it? So it's Vx plus I vy. Okay? So that's equal to, let's write some alpha. Alpha is a number. Okay, let me put e. I'll use my notation. Okay, then e raised power minus I omega. Just exponentiate this constant. So sure? Clear? Okay, so now tell me what should be the nature of this a. This a is in general a complex number. It's a constant, is it? It's a constant of integration. So it should be in general what? A complex number. Clear? Is that true? Look here. So this y naught should be in general a complex number. In general, it can be real as well as in general it should be complex because I am solving a differential equation for a complex variable. Okay, let me put this a. Okay, so a is in general a complex number. Okay, so let me write this a as some e raised power I alpha kind of thing. So is this a complex number? E raised power I alpha. So it's cos alpha plus I sin alpha. Okay. Let me put some another real number. V0t. Let me write this way. So V0t is a pure. It's a real number. I need to figure out what exactly this V0t. What is how many unknowns are there now? Alpha and V0. Is it? So you are having a complex number. How many unknowns for complex number? 2. Is it? So that's why I have put it in terms of 2 unknowns. Clear? So it's the same thing. The way you are writing complex number, let's say you are having z is equal to z is a complex number. You write e raised for I theta, r and theta. Got it? You think this v0 as r and this alpha as theta. Clear? So there is a meaning for this v0. Why I have put it this way, v0t from this very context. Okay, now let's write it. Okay, so which implies Vx plus I, but I need to figure actually what Vx and Vy is it? I need to figure them individually. So let's write it as V0t e raised for, now I alpha is there, so you put minus I omega minus alpha t. You can put alpha equal to 0. Alpha is a phase, you can put alpha equal to 0, or you can put minus I alpha. Let's write minus I alpha here, so that to make to look this nice. Instead of omega minus alpha, I will put as omega plus alpha. It doesn't matter. So you put a minus sign here, a plus sign, it hardly matters. Okay. Now let's write in terms of the components. So I will be having cosine of omega plus alpha t minus I sine of omega plus alpha t. Okay, so what it is? So Vx is equal to V0t cosine of omega plus alpha t, and Vy is equal to minus V0t sine of omega plus alpha t. Is that true? So these are the parametric equations of a circle, is it? So that means this velocity vector, its tip seeks a circle in xy plane. So isn't it? So it is actually x is equal to r cos theta, y is equal to r sin theta kind of thing. Is that true? So that means that the tip of the velocity vector sweeps a circle in xy plane. So it's a parametric equation. Now you look here. So you can write Vx square plus Vy square. That's actually equal to V0 t square. Is it true? Now we got now what this gives me. This gives me the magnitude of the velocity. Is it? V0 t represents actually the magnitude of the velocity in xy plane. So let's say you start with a particle. It's having three components of the velocity, Vz and Vx, Vy. So this V0 t will give me just the projection of the velocity in xy plane. So because it gives me the length of the velocity vector only in where? In xy plane. Got it? So okay, now if let's say if I make this velocity to be the momentum, let's multiply those factors with which it becomes momentum. So it will give me then the projection of the momentum in xy plane. Clear? So we will see it in a moment. Everybody got it?
Yes.
What I have done? Okay. So this alpha will be simply the phase with which the it will simply depend when you inject the particle into the magnetic field. Okay, what kind of phase it occurs. Okay? Clear? So this V0t is actually a constant term. Is it clear? So V0t is a constant, it will stay constant throughout the motion. Now what we are interested in actually finding the trajectory. So okay, so let's write from here. So I can write now dx by dt, that's equal to V0t cosine of omega t plus alpha. Now like was t others. Like this thing. So you people don't look carefully. Eh? Isn't it? So you just put e raised for I alpha here. What you will get? Omega t plus alpha. Alpha does not have t. Eh? Alpha is simply the phase. Eh? So now tell me, once you solve this very equation, or better, what you are looking? Any problem? Okay. Just solve this very equation. Just tell me what is the solution. Just tell me what is the solution. So I can write this x of t. Okay. You just integrate it out, is it? So once you integrate out, so what will be V0 of t? Then what is the integration of cos sine omega t plus alpha, then divided by omega, is it? So this will be right, and there will be a constant of integration. Clear? So let's write that constant of integration to be x0. समझ आया? So now from this very equation, I am having dy by dt is equal to minus V0t sine of omega t plus alpha. Now tell me what I can write. So where x0 is constant of integration. Okay, and it will give me the initial coordinate, initial position of the particle. So at t equal to 0, the particle is located at x0. Okay, so y of t is equal to y0 minus y0 plus v0t by omega cosine plus y0 is also the constant of integration. Clear? Now let's write any question till now? Yes? Yes?
What again, sir? X0 is?
X0 is constant of integration. Okay? So it is simply the initial condition. At t equal to 0, particle is at x0 and y0. Clear? So now let's define a quantity r as the radius of the circle. If you see, it's actually the x is actually x and y, so it is the parametric equation of the circle again. Is it? Is that true? So since we are solving only the xy plane motion, I have not taken yet the z motion. Is that true? Okay. So it means I am having a circle where? In xy plane. So that means particle in a magnetic field covers a circular track. Okay, in an xy plane if the motion is in xy plane. Okay, so the circle is having a radius. Let's write that radius to be r, and it will be simply v0t by omega. So now tell me what is omega is the cyclotron frequency, is it? So let's write the cyclotron frequencies. So it will be ECB. Okay. So this I can write now. So let's multiply this C here. It will be C square B by epsilon. So I can write it as like this: CPT by EB kind of thing. Okay. So why PT? What is the PT? Can you tell me what is the PT from here? Just tell me. Just tell me what will be PT. So it is simply V0P, then it's epsilon divided by C square. Is it true? So what this is actually the momentum. So that means PT will be the momentum along the transverse direction, is it? That means in the XY plane. So this is the projection of momentum. XY. Okay. So therefore I can write this X of P. Okay. So you can put V0 of T in terms of, so I write X0 of T minus this thing plus Y of T minus Y0 whole square. That's actually equal to. So it means, so R is the radius of circle. So in XY plane, so you are having a circular motion, and the center of the circle is simply X0 and Y0, and R is the radius. Clear? Now let's look at, you are having actually Z motion as well. So that I have to note that equation yet. So you had this V's dvz by dt, that's equal to 0. Is it true? So let's solve it. So it gives me Vz is equal to some V0 along Z direction. So it's a constant velocity. Okay? Along Z direction. So Mujafar? So now let's solve this thing. So it will be dz by dt. So I have not assumed any zero component of the velocity, is it? I assumed all the components are non-zero initially. So it will be simply these. So what it gives me? So it gives me the trajectory along Z direction. Some Z0 plus V0 Z T. So what it will give me? It's a linear equation, is it? So what it will give me? So you are having a circle, let's say. So this is XY plane. You are having a circle like this thing. Okay? A particle is moving in, let's say, in this direction. Okay, now you are having a motion. So consider this as Z direction. Okay, so you are having this as Z direction. What this will give me? It will give me the motion along Z direction, is it? So it will push this thing along Z direction. It will allow it to move. So it will follow them. So this kind of, what is this trajectory? So it's a helix. I have plotted it wrongly. So it's a helix. Okay? So Samsha, it is simply a helix like this thing. So that means this will allow the particle to go along with a helical path. So with a constant, every step of the helix is having the constant radius. Radius is constant, it is not changing because the projection of the momentum in XY plane is constant, PT. Okay? So R is a constant vector. So that means it will be the same helix throughout. Clear? So in magnetic field, if you are having Z motion as well, okay, the particle is moving along Z direction as well, you will be having a helical path. If there is no motion along Z direction, then you are having simply circular track. So that means if you are having a perpendicular magnetic field, the particle only moves in XY plane, then the motion is circular in nature. Clear? Now let's take modification to this thing. So the question what we posed in the last lecture. So let's try to. Okay, so I have considered here. Yes. Any question? Get any question? So you are not comfortable in the class? Huh? I feel you are not comfortable. Any problem? Yes. You can tell. No problem. So here I have considered the motion. Oh, sorry. Here I have considered magnetic field to be uniform and constant. Is it? Now let's allow magnetic field to change very slowly in an adiabatic way. Okay? So that means at every step of the flex, so let's assume the magnetic field changes very slowly in comparison to the radius of the helix, okay, and in comparison to the step size. So that means along this distance the magnetic field appreciably does not change. It remains constant along the step of the. So that means you can see from one step to the another step, magnetic field is essentially constant and uniform. But once you move along the complete trajectory, you will see actually magnetic field is changing, is it? So sure? But the change is very slowly. In classical mechanics, if you are changing, okay, so here it's actually the periodic motion, is that true? It's a circular motion, it's a periodic motion, clear? So if you are having a periodic motion, okay, in classical mechanics, if you are having periodic motion and you change the conditions of the motion slowly, or we call adiabatically. So there exist certain quantities which remain constant or invariant throughout the motion. So those quantities are fixed for the motion. So you move from one step to the another step, those quantities will be the same. Okay? So we call those as adiabatic integrals or invariants. Okay, let me give you an example. So you are having one adiabatic integral to be this P dot, where P is generalized momentum, R is actually the canonical conjugate coordinator. So like this thing, you are having L d theta. Okay, let me mark that dot here. So like this E d t. So these are the adiabatic integrals. So why it means over a closed path. I mean along what periodic path. Clear? So so these kind of integrals, they form what we call as adiabatic integrals or adiabatic invariants. What I mean by that, if you change the conditions of motion slowly or in an adiabatic fashion, then these quantities remain same throughout the motion. So much on? So these are the quantities at hand. Okay, now let me take this very object. This kind of adiabatic integral. Clear? Okay, so I will take the adiabatic integral to be, let's say 1 by 2 pi, so because I am taking along the circle. Okay. So this P dot, where P is the generalized momentum. Generalized momentum. Clear? Since motion is along which axis? It's along z axis, is it? So you are having a circular track in xy plane, but the circle moves along z axis, is it? So that's how it forms a helix. Is that true? So tell me what would be the momentum here? So it's actually the momentum that's in xy plane, which. So now tell me what kind of momentum you are in. So what momentum it is? So it is a generalized momentum, so it will be actually the transverse momentum, which helps the particle to move. Okay, let me write first. Okay. So let me write. So like this thing. Pt and dr. Okay, so this is actually the projection of the generalized momentum. Because you are having the motion a circular where periodic it is in the xy plane. Is that true? Clear? So now tell me, so if you remember what is the generalized momentum, so P is equal to that small plus E by C A. You people remember? So this is the generalized momentum. So I can write then 2 by integral this pt plus a by c. Clear? समझ रहा? So where this PT is now? It's in the XY plane. I have shown you. C is that R is in terms of this PT is a projection of the momentum in XY plane. Okay. So now let's write it. So you people got the idea what I am trying to do, because this remains, this kind of quantity remains invariant throughout the motion. So that means if I start, let's say t equal to 0, and some after time, at some time t, so I will be same as I, is it? So that means I can compare different quantities of the motion, okay, at different times, because this very object remains constant. Okay, so you will see in a moment, you will appreciate the result. Okay, so let's write it. So that means this I is equal to 1 divided by 2 pi. So I get integral P dot dr, okay, plus E by 2 pi C integral A dot dr. Clear? Okay. So now tell me, what about this PT? Since PT is the projection of the momentum in XY plane, and we have seen this momentum is actually constant. Is that true? So what was that equal to? It is actually proportional to V naught P, if you remember it. So V naught is actually a constant. It remains constant throughout the motion. So it means this very object is constant throughout the motion. Clear? So this is constant throughout the motion. Now tell me, if I take this PT out, since this is along a circular track, is it? So the integration is along a closed curve. So here the closed curve is a circle, is it? So now tell me, what about this very integral? So I can take this PT out, divided by 2 pi. So it is simply integration over dr. So that will give me 2 pi r. R is the radius of the circle, is it? Okay. Plus E by 2 pi c. Okay. Now look here. So it's along a curve. Let's say called some curve C. So let's call this along a closed curve C. You can now apply the Stokes theorem here. So line integral you can convert to the surface integral. So I can write it over some surface. Okay, S, and curl of A dot ds. Clear? Everybody followed it? Okay. So what this is? So it is R dt. Okay. E by 2 pi c. Can you tell me what this object is? Okay, here if you see the helix, what we have, so it's actually, the particle is going in the anti-clockwise direction. Is that true? So you start with the particle, it moves like this thing. Okay? So this is the direction of the helix. Clear? And magnetic field is along which direction? Along the same direction. Now I need to calculate curl of A is actually the magnetic field. Is it? So I will write it simply as B dot ds. Clear? So B is, now I need to figure out what is the direction. Direction of this B. Is this B opposite to this curl of A, or it is in the same direction?
Same.
So it's actually in the opposite direction. So this curl of A and B is having actually opposite direction. You just look at it. So this is the helix and this is the magnetic field. Okay, so that means the velocity vector is in this direction, field is along in this direction, the B, is it? So you need to check actually the direction of this curl of A. Okay, so you get a minus sign, a change in sign. So just check. Okay. Now what is B? So this B is the magnetic field, is it? So since it is what? Can you tell me? It's actually the constant field. Since we are choosing what? Magnetic field to be constant. Okay, although it changes slowly, but it's what?
Slow.
It's constant over the step size of the helix. Clear? So so that means I can take it out. So I can write this R dt minus E by 2 pi c. So I can simply write it as B. Then you are having integration over a surface. What it will give me? Surface area. Okay. So how much is that? Pi r squared. Okay. So it will be simply area of the circle. Okay. Clear? So much. Okay. let's write it. Let's write this R in terms of since our R is equal to C PT divided by E times B, okay? So therefore I can write this I. So substitute for what? R, okay? You substitute for R here in both the terms, so what you'll get ultimately? You'll get I is equal to C PT square divided by twice E. So now this is the value of this adiabatic integral. So it means, now look here, so this is a constant term, is it? So I is constant throughout the motion. Clear? So that means this PT and B, they should be proportional to each other. So when, okay, like this thing, so I can say since PT square, so which gives me PT square is equal to twice EI divided by C multiplied by B. Because B is, although B is constant over the step size, it's varying. It is still varying. It is slowly varying, is it? So now this is a constant term. Twice EI by C, is it? So it means the momentum along. So it is the transverse momentum. The momentum, the projection of the momentum on XY plane, it's proportional to root of B. So that means the stronger the field, the stronger the momentum. Okay? Got it? Okay, now let's calculate what is R. R is actually C, okay, from this very relation, I am having, okay, so R is actually C PT by EB, is it? So now what is PT? It is actually proportional to, okay, let's write PT. So it is C divided by E, okay, by B. So it will be simply what? Twice E I by C, its root, and then you are having root of B. Okay? Clear? Is it true? So it means R is, the radius is inversely proportional to this B. Huh? Is that true? So that means as, okay, so as you go, okay, so as you move in the field, in the direction of the increasing field, okay, let's say the field increase in this direction, is it? Summation, what happens? Radius decrease. Last time intuitively we said it should increase, is it? But it's not that, it's actually decreasing. So you are having, you start with, let's say, circle of this very radius, then what will happen? So the radius will decrease. Like this thing. So this is how it will go. Clear? So radius of the helix will decrease. Samajh aaya? So if I slowly change the magnetic field, so yes, it will reach. Okay, now if the field at certain point becomes strong, is it? Because at sufficiently large distance you will be reaching to a strong field, is it? So wire, it will be simply what? It will reach to the radius equal to 0. So that means at that very point it will get reflected. So that means it will not penetrate. Okay, let me show you that. Okay, let me tell you. Okay, since in this entire system, energy is conserved, is it? So you are having energy conserved in this series system. So when you are having energy conserved, so it implies this P square is also conserved. Okay, momentum square. Huh? Clear? So now let's write this P square. P square I can write as the projection along the transverse direction plus the longitudinal direction. Longitudinal momentum would be what? It's the momentum which allows the particle to move along z-axis, is it? So this is actually along the z-axis and this is in the xy plane. Clear? So now if this is conserved quantity P square, is it? Tisha? So this is a constant term. Is that true? For throughout the motion this is conserved. Okay? Conserved throughout motion. So what it means? Let's write PL square. So that will be simply P square minus P square T. Is it transverse momentum? Now tell me what is P square? Okay, P is actually proportional to root of B. Okay? So let's write it as some p square minus some constant c, okay, and clear? So summation where c is constant of proportional to, okay, it is here, so I can write p is equal to some c root of b. Clear? समझ आओ? Some constant of proportionality. Now look here. So if you want the particle to move along, let's say z direction, PL gives you the motion along z direction. Now this PL square should be positive, is it? समझ आओ? Clear? So this must be equal to what? Greater or equal to 0. So if PL is equal to 0, let's say, that means there is no motion along z direction. Clear? So there is no longitudinal momentum, particle will be only in the xy plane. Clear? Now if it is greater than 0, so that means particle is having z motion. Now since I am increasing b slowly, okay? So if we increase this thing, okay? If we increase it in such a way, such that the value of this very quantity, the magnetic field reaches to a point where this quantity is same as where? This p square, okay? So it means at that very point this PL becomes 0. So what does it mean? So the particle stops, is it? So once the particle is stopped, so that means we have reached to a very high magnetic field, okay? So it means the particle will not penetrate through a very high magnetic field. It will simply get reflected back from that very point. समझ आओ? You got my point? So that means a charged particle, if it is moving in a very high magnetic field, it may not penetrate through a sufficiently high magnetic field. Okay? Clear? So this is actually the result we have arrived from the adiabatic integral. Clear? Any question? Huh? Any question? So how much time remaining? So this was all discussion about this charged particle in electric and magnetic field. Now the assignment I have already asked you to do what? So take the particle in the electromagnetic field where you are in both electric and magnetic field are non-zero. Consider electric field along x direction, magnetic field along y direction, then do the analysis. Okay? Okay. So let's go to what we call a Lorentz transformation of the electron. Shall we stop here?
Yes, sir.
Huh?
Yes, sir.